Welcome to Web Handling. My name is Dave Roysum. In the previous clip, we left you hanging. We did not give advice for stroke, speed, or shape of oscillation. We could not, because the web industry had not really studied it. With this simple new model, we can now provide some practical guidance on how to set up oscillation and what limitations there might be. No web is perfectly level with regard to thickness profile. While caliper variations in the real world are complex and depend greatly on the process, most have one important characteristic. That is, manufacturing converting both tend to be quite streaky. By this, I mean that the CD variation tends to be quite stable with time. The streaks may persist for the better part of a finished roll, many rolls, or many days until some worn part is repaired. Or it may even be a feature persistent since the first day the machine ran until the day it is finally retired. These figures from FP Innovations show the near universal trend of streakiness, of basis weight, thickness, bagginess, and in the case of paper, moisture. An entire book by Paul Frost is dedicated to the statistics of these and other trends for the purposes of quality control measurements. Another common trend is that the thickness profile problems that cause the most trouble tend to be high lanes. These ridges could occur in the middle or at the edge of a wound roll. Yes, it is true that corrugations are at a low spot, but the principle of oscillation is effective in either case of high or low. In any case, as we've opined on many occasions, the range of caliper variation tends to be around 1 to 10%. At 1%, you might have no problems. However, at 10%, you might have no product. So, we can take the well-studied streakiness of webs and simplify it to a center ridge and an edge ridge cases, and we have something that can be studied. If we need more complexity, the method shown next will accommodate that quite easily, though those results would necessarily be confined to the particular profile studied and would not be generic as we have here. There are many possible ways to study oscillation. Here we have chosen to use a spreadsheet because it is much more accessible and better known than computer programs. Shown here is a tiny portion of a spreadsheet showing the essence of the technique. Though it is difficult to make out the numbers, it is easy to visualize the two essential elements of the technique. The first is a sine wave-shaped caliper variation shown as columns. Not seen here is the very wide flat profile on either side of this gauge band and a raised edge on one side. The second feature is the sine wave oscillation shown as rows. A little more than half a cycle is shown in this screen snapshot. Not shown is the bottom row that simply sums the thicknesses of the layers above. Notice that the system is discretized, as is common in winding models and finite element alike. Here the defect is modeled 18 units wide. That could be 18 millimeters, 180 millimeters, 1800 millimeters, as we have non-dimensionalized the width. Similarly, the oscillation is also non-dimensionalized. It has no less than 18 rows and has many more for wider oscillation. The technique shown here is quite simple and quite adaptable. The user is completely free to make a finer mesh if they desire. The user is completely free to make any shape of profile and oscillation that they wish. Indeed, I modeled the slitter lip as an exponential shape. The results of the model are more than plausible. They are exactly what you might expect. As the oscillation stroke increases, the effective height of the defect decreases. What is new here is that now we can put numbers on it. The sometimes heard recommendation of oscillating the width of the defect does give a noticeable 50% decrease, but the user may want to consider 2 times or 4 times the width. However, this magnitude of oscillation may be economically viable only for narrower defects, with the exception of blown film die or tower oscillation that is not limited in that way. This is also in line with field practice, where oscillation is used primarily for narrower defects such as corrugations and narrow ridges. The results of the model are more than plausible. They're exactly what you might expect. As the oscillation stroke increases, the effective width of the defect area increases. Thus, in a very real sense, we are trading off an increase in the affected area for a decrease in maximum severity. The raised edge, such as perhaps due to slitting, has similar trends. The maximum defect intensity is decreased while the overall width is increased. Perhaps what might be surprising is just how effective oscillation is for raised edges. First, the defect tends to be much narrower to begin with. Second, the same relative stroke is somewhat more effective. Here, we summarize the graphical results with words. Oscillation is very effective in reducing maximum intensity, but you may want to try to go a bit beyond the 1 times the width of the defect. Also, even a tiny oscillation seems to be very effective for raised edges due to slitting or perhaps other causes. What was studied, but not shown in the previous graph, was one other perhaps surprising conclusion. That is, shape doesn't seem to matter. A step-shaped thickness profile, if one could even be made, is almost the same as a sine-shaped thickness profile. The same is true of oscillation shape. Sine is almost as effective as zigzag. In hindsight, this now makes sense. Oscillation is a blurring and smearing process. Shapes become indistinguishable as they are oscillated. Think of this like the shapes of a photograph that are difficult to see with motion blur or with very slow shutter speeds on a handheld camera. Indeed, if you look at the previous graph, you will see that the sine-shaped defect starts to get a flat top as oscillation strokes increase beyond about 1 wide. No less important as oscillation stroke and shape is oscillation speed. If you oscillate too slow, the damage of the buildup of extra thick layers is already done before it has moved very far sideways. If you oscillate too fast, you can run into wrinkling and offsets on the wound roll edges as detailed in the white paper. To analyze speed, we can start with a simplification. That is, that only 1/2 cycle is needed for effective smearing of streakiness because the other half cycle is just a mirror image and does nothing new. The next simplification is an assumption that must be made in order for the problem to be tractable. That is, how much influence does layer 10 or 100 or layer 1000 beneath the surface matter compared to the current outer surface layer where most of the damage is being done. Here I rely on many published studies that show for the most ordinary sized rollers that are anisotropic, the outer 2 centimeters is where most of the radial and tangential stress gradient occurs. Here I rely on some unpublished studies at Beloit that for typical paper grades anyway, most of the influence on roll hardness comes from the outer inch. Given those assumptions and an exponentially weighted thickness with depth profile, we can tentatively make the following guideline. That is, oscillation becomes very ineffective if the speed is such that less than 1/2 cycle is made before an inch is added to the radius or 1 times wide. The width Given those assumptions and an exponentially weighted thickness with depth profile, we can tentatively make the following guideline. That is, oscillation becomes very ineffective if the speed is such that less than 1/2 cycle is made before an inch is added to the radius. The white paper takes these parameters and gives some example calculations. It shows that it may be difficult to oscillate fast enough just above the core on thicker materials. It also shows that it may be difficult to oscillate fast enough on current blown film designs to avoid damage such as ring stars if the gauge band is a noticeable fraction of the bubble's circumference. Thank you so very much for watching this module in my Plant Practical video series. Stay tuned for even more advanced and niche web handling topics in this Web 201 series. Let me know if there's something that you would particularly like to hear about.